This is the first of two videos about torque. This one is about the full vector definition that appears in section 11.2 of our textbook. That definition is the torque is R cross F, where the result of this calculation is a twist that can cause angular acceleration around the axis defined by the vector tau. That twist has units of Newton meters. The vector R is the vector that points from the axis of rotation to the point where the force acts. And if, as shown here, the force is acting counterclockwise with respect to R, that corresponds to a positive rotation around the direction of tau. The cross here indicates the vector cross product. It is not multiplication. It's a special kind of calculation involving two vectors where the result of that is a vector that points perpendicular to both R and F. And that direction is given by the right-hand rule. When, like in my previous picture, the rotation is from R towards F is counterclockwise, the direction that your right hand curls, then that torque is out of the page. That is in the k-hat direction if we were looking at this in the xy plane. As I said before, torque is a twist around an axis defined by the direction of tau. It's plus if it's counterclockwise around that axis, negative if it's clockwise. That counterclockwise direction is chosen to match the angle theta that we define in polar coordinates, where that angle theta goes from the x-axis towards the y-axis in a counterclockwise direction. One important detail is that the torque is zero if the R and F vectors are parallel. It's maximum when those two vectors are perpendicular to each other. Now, I introduced the general rules for calculating torque in this course because you'll use them in Physics 2, where it's used in magnetic field forces and forces due to magnetic fields and the calculation of magnetic fields, and in Calc 3, where it's done as a purely mathematical exercise, both preparing you for its use in engineering mechanics as an engineering major and also in anything that you do involving electricity. I'll present here just two basic methods that are using the FOIL method for multiplying out two expressions that are effectively a multiplication but actually involve the cross product. I also give another one at the end of the video. The most important thing to realize is that this is not like normal multiplication. It is not commutative. It's essential that you write out the formula and put each vector in its correct place, R first followed by F, before you do the calculation. If you don't do that, you'll get the wrong sign for your answer. Now, one of the memory tricks is to remember that this is a rotation type of thing. There's a sort of curl involved from X to Y to Z. And if you already know that that order is X, Y, Z, and that theta curls from X towards Y around the Z-axis, you can use this little circular mnemonic to remember the result of whether the result is plus or minus. Separately, you have to learn that I cross I is 0. Okay, the way this works is if you write the ijk in a little counterclockwise loop, if you have to move counterclockwise from the first pair to the third vector, then the result is plus. So if you go from I towards J, the next one is K, and if you're going counterclockwise to do that, the result is plus. If you go from J to K, the next one is I and it's plus. If you go from K to I, the result is plus J. If you have to go the other way, if you have to go from J to I, which is sort of the wrong way around the loop, the result is minus. So J cross I gives you the negative of K. If you go from K to J, the wrong way, that gives you negative I, and so forth. Another way to remember this is just use the number line where right is plus. If you write XYZ, XYZ, IJK, IJK, if you have to move from to the right for that particular pair, then the result is plus. So as you see here, if I go from I to J to the right, I get K, which is plus. So the way that works is for I cross J, IJK is to the right, so plus. JK, next one is I to the right, is plus. K cross I is plus. If you have to go to the left, the result is minus. So if I have them in the wrong order, instead of IJ, it's JI. From J to I to the left gives me negative K. Instead of JK, I've got KJ. To the left is negative I, and so forth. just as a little bit of a different perspective, if you write out the times tables for the dot product and the cross product, this might help you realize just how different these two things are. The dot product is just ones down the diagonal. I dot I is 1, J dot J is 1, and so on. In the cross product, I cross I is 0. The diagonal elements are all 0. And notice the alternating signs as you go across this table because of the fact that the multiplication is not commutative. I cross J is K, but J cross I is negative K. A mathematician's view of this is that this is a non-commutative, that is a non-abelian algebra. Physicists refer to this as being anti-commutative, where anti signals the fact that when you commute the two operators, you get a minus sign. Okay, there's a simpler approach when both vectors are in the xy plane rather than some arbitrary direction. That will be taken up in the next video. Finally, if you want to know how to do the thing in the most general fashion, the most general fashion is to use a matrix and evaluate the determinant of that matrix. The matrix is constructed with unit vectors across the top, the first vector on the second row, and the second vector on the third row. This is covered in Calc 3, and if you've got truly messy vectors where all of the components are non-zero, this is the best way to do it. When the vectors have a lot of zeros in them, only a few non-zero terms, then the methods I just showed you are easier and faster to use than constructing the determinant. This is the way it looks. If it's R cross F, it's important that you have, again, the vectors in the correct order so that R is in the middle row and F is in the bottom row, and then you just evaluate that determinant. Okay, and I close with the usual frame showing where these figures came from.